In this section, we're going to talk a little bit about Wireshark's graphing capabilities. And I think they're really, really strong and really effective at helping you troubleshoot certain types of scenarios. And we'll go through many of those scenarios later. But in this section, I want to demonstrate a few of these different types of graphs along with examples of when they might be useful and how to interpret and create them. I think that's really important. Now, to speak to visualizations a little bit at a high level, visualizations can be really useful when used correctly. That said, visualizations are not always appropriate. Sometimes data is best served just in a table, just as it is. We've looked at some examples of that, right? Like we've looked at conversations, we've looked at endpoints, protocol hierarchies. Those aren't visualizations, they're just tables of data, and that's okay. I think there's a tendency for practitioners in IT and in security to want to visualize everything, and that's really not the best approach. You only want to visualize when it actually makes sense. So when it actually helps you make a better decision when you visualize data, that's when you want to do it. Because that's all we're doing here. Remember, we're just asking questions, getting answers, and making decisions based upon that. If a graph fits into that and it's in place, that's great. Let's use it. But if it doesn't, rely on the data. But with that said, let's go ahead and jump in here, and we're going to look at a few different graphs that can be useful for you. The first graph I want to look at is Wireshark's I/O graph. Of course, I/O stands for input-output, and it's going to show us a display of the throughput, the amount of communication occurring over time. There's really no other way other than a graph to really visualize that well, at least over time. We can look at an overall throughput statistic, but we're talking about over time, and graph is a good way to do that. Now, to get to this data, pretty straightforward. We're going to go to statistics here, and then we're going to go to I/O graph. I'm going to go ahead and expand this out a little bit. It starts it out pretty small. It takes a little second to load it up, as you saw. But this is a pretty neat graph, and it shows us some pretty useful information. There are a couple different things going on here that we need to look at and kind of be aware of. We have two series of data going on here, first of all. We can see those listed down below. The black line we see here, the color is black and the style is line. Of course, we see that here at the top, is showing us the number of packets per second. In this case, the x-axis is time in seconds, of course. So we see 0 all the way to a little over 150 here. So that's seconds. And the y-axis is packets, which means we're looking at the number of packets per second. And we're essentially looking at it kind of a view of the throughput. Packets per second isn't throughput per se. That would be more bytes per second. But nonetheless, we're looking at something assimilating to the amount of communication going on per second. Of course, you see that's pretty high. At least we see that at least a consistently relatively high level between 400 and 600 or 700 packets per second consistently throughout this capture. There's a little dip here around 100 seconds. And then, of course, right at the end, we go down to 0. Now, if you look at the name of this capture, you'll see it is download fast. So as you might suspect, this is a single file being downloaded relatively quickly and successfully. So that's pretty cool. The other series of data we have here is named TCP errors, and you see it's based upon a display filter. So we're showing a display filter, TCP analysis flags, which is going to show us all of the TCP errors in a blue bar chart marked in terms of the number of packets as well. So again, we're looking at packets per second, but instead of the line here, we're seeing these bars, which are showing us the number of TCP errors. And we see there's a few of those. There's not a lot. There's some of those occurring at certain places. You can see that in some cases, they kind of are simultaneous with these dips. So we see this dip around 100 seconds, and we see a prevalence of TCP errors. So there's a chance those are related. I can tell you they probably are. Having looked at this capture, you can certainly go and dig into it yourself a little bit. But it's a pretty good illustration of how we can plot multiple data sources in terms of I/O. Now, we can click around and move around in this if we want. We can specify different things. I think one of the things that can be useful is to click into here where it says y-axis, where it says packets, and we can actually change that to bytes. Now, the thing is, if you're going to do that, you might want to, you're going to have to probably lose your extra data series, right? Because at some point, then we're mapping bytes and we're mapping packets, and that isn't going to work so well. So we're missing that. But nonetheless, this gives you kind of throughput. We see our intervals change a lot. We're now looking at quite a bit more data in that regard. And because of that, because of the scale, it makes it to where we can't see our other data series. But you can do that. I'm going to go ahead and for now just change that back because packets kind of gets us what we're needing to see for the most part. So we do have that option. We have a couple other options down here. We can say that the mouse either drags or zooms based upon our clicks. We can change our interval. Here we're at 1 second. I can go ahead and change that to 10 seconds. It's going to redraw the graph. It's going to make it a little harder to see some of these TCP errors down below. So we're not going to leave that. I'm going to go ahead and change that back to seconds because I think that's most appropriate for this example. We can plot the time of day as opposed to the seconds relative to the beginning. So here we're seeing time of day. It looks like this occurred in the 1300 hour. Go ahead and uncheck that there. And we can put this in a logarithmic scale if we need to here. Not necessarily appropriate for this example, but we can do that as needed. So pretty cool display of this normal file transfer occurring over what looks to be maybe 150, 175 seconds. Now, graphs are really great like this for measuring a value over time, of course, but they're also good for comparing things. Certainly, we can compare things within a single capture file like we are here. We can add additional data series. If we had multiple downloads going on, we could specify a display filter based upon a single host and map that individual host and maybe plot it in a different color. But these graphs are also useful for comparing things that should be similar but are not. So look at this graph, and of course we see here we've got a lot of packets. It's very consistent over time, and then the file finishes and it dips down to 0. This is called download fast because the file was downloaded quickly and successfully. But let's switch over here to another capture file, which I've called download.slow. In download.fast, I was in the US and I downloaded from a US server, and it was snappy and got me the file quickly. In this capture, I'm downloading another file. It's actually a Linux distribution, but I'm downloading it from the US, or I'm in the US, downloading it from an Australian server that's really struggling to keep up. So you can probably picture in your head what the IO graph might look like, but let's actually pull it up and validate those thoughts. Now, in this case, the IO graph, we have a lot fewer packets in general, whereas we had several hundred. Here, we're only looking at 90 packets as well. Now, again, packets per second isn't necessarily the greatest indication of throughput, but since we know this is exclusively a file transfer, we know that these are data packets, so they're all kind of around 1,500 bytes. So in this case, we can kind of relate those together. Now, in this case, not only do we have a fewer number of bytes altogether, as we can see by the upper bounds of this graph, we can also see we have a lot of these really significant dips. Right here, a little after maybe around the 35-second mark, we have a dip that goes down to 0. So at this point, communication is actually stalling completely. No data is being downloaded. We see another significant dip here around 60 seconds. This is accompanied by some TCP errors here. We see another dip here around maybe 90 seconds, another one around 120, several of these. So we have a lot more variance as we look at this graph from left and right. So that's significant, and then it shows how this slow download process is stacked up. So this is a good way to demonstrate when you might have a latency issue that's occurring either on your end or on the server end. Now, a cool thing I can do here, since I have two captures open with two different graphs, is I can actually stack these up side by side. So let's go ahead and do that real quickly. So I'm going to go ahead and resize some things here. And I've only got a limited amount of screen space here, so I'm going to be a little limited, but not too bad. We should be able to get these things stacked up pretty closely together. There we go here. All right, so they're not perfectly the same size, but you can kind of compare these together. So on the bottom we have download fast, and it looks like it's pretty darn consistent. And on the top we have download slow, and it's obviously not. We see these big dips. Now, when we decrease the size of these things, you have to be careful, and this is with any graph, that you pay attention to scale. Because if you could obviously see the dips here. We can see that there are dips on download slow, and that means that the download is struggling a little bit. And we don't have those on download fast, right? So that would be one level of concern. We would see that, okay, well, there's clearly some things going on here. But pay attention to the scale as well. This scale for packets per second goes up to 90, right? So the maximum amount of data being transferred is limited pretty low. Here, the scale's up to like 700, right? And we're hitting that in a few places in bursts. So the scale matters a lot too. So when you're looking at these graphs, you really have to be concerned with the scale you're looking at. Now, of course, you can change that scale. We could try to put that on similar, try to put that on like a logarithmic scale or something like that. Try to get it closer to what it needs to be similar. But for the most part, these are going to be different, and that's okay. You want them to be different. You want this to auto scale so you can get the proper perspective on dips and things like that. But still, pay attention to scale when you're looking at these graphs. It's very, very important to make sure that you're making accurate assessments about what you're seeing. If I were to zoom out on these far enough, these dips that appear in download slow would kind of start to go away. So without looking at scale, you might miss an example of when you have latent communication going on. And of course, we'll look at this in a little more depth later when we talk specifically about troubleshooting latency in a later module. So I've switched over to a different packet capture now. This is http espn.pcap, and I want to use this to show a practical example of something you might do that's a little bit more unique with an IO graph. And in this case, we're looking at ESPN because it's one of those sites where you visit it and you're not actually going to one site, right? Like you're pulling data in from a lot of different places because there's a lot of different content delivery networks and advertisements and things like that going on. When you browse to a web page like ESPN or like a news site like a CNN or a New York Times or Washington Post or Fox News or what have you, you're actually communicating with a lot of places, pulling in a lot of different stuff. So what may sound like a pretty simple thing is pretty complex. You can see here we have 956 packets down here listed at the bottom. So this is it's a lot of data, right? It's a lot of information being pulled back for a visit to a single website. So an IO graph can actually help us characterize to some degree the distribution of traffic here. And in this case, I'm specifically concerned about the distribution of traffic between the primary content provider, so the ESPN owned data, versus the extra content providers. So the content providers that are pulling in things like ads and external media and things like that. That's the data I actually want to understand in terms of bytes, the relationship between those two things. It's a useful exercise. It's something you might find yourself doing practically when looking at certain types of scenarios. So we're going to run through that here. Now to do this, the first thing I need to do is to understand the primary content provider. And there are a couple ways to do that here. But the way I'm going to do it for our purposes is to actually look at something we've already looked at here and go to the conversations screen. So I'm going to go to conversations here. And I'm going to look at my IP conversations. I'm going to sort those by number of bytes. Now, in this case, we see 172.16.0.122, and that's actually our internal host. That's the source web client that's browsing to the web server. And we see here that the top talking host by a long shot is this 205.234.218.129, which is our primary content provider. It's where most of the content from ESPN.com, in this case, where it was coming from. So that's the IP address we're concerned about, and we can actually use that IP address to start to build our IO graph. To do that, I'm going to go ahead and close out of this window, and I'm going to go ahead and go Statistics, IO graphs. And in this case, we're going to get a graph that's pretty similar to, or it's the same at least style of graph we've looked at before, right? It's going to show us all the packets mapped with packets per second, and it's going to show us any TCP errors. In this case, the graph is pretty boring. It doesn't really have a lot that's entirely useful to us. But we're actually going to modify this quite a bit. So the first thing I'm going to do is I'm going to go ahead and just get rid of both these data series. I don't need them. I'm going to start from scratch here. Now I'm going to click, I did that by clicking the minus. I'm going to click the plus here and add a new data series. And I'm going to call this top talker. And what we're saying here is this is our top talker, that 205 IP address that we saw. And we want to map all of the data that we saw there. To do that, we're going to apply a display filter for the IP address. It's 205.234.218.129. I'm going to go ahead and expand that out a little bit where you can see it. And we're saying, show me all the data related to that particular IP address. We'll pick a color that's really easily noticeable. Let's go with just bright red. And we're going to change. We're not going to do a line. We're going to do a stacked bar, and that'll make sense here in a little bit. And then we're going to change this to bytes per second here. So we're going to go ahead and put that there. And then next, we're going to go ahead and add, let's go ahead and check this box here so you can see it. So I've enabled that here and you see that data. So we're looking at the amount of time in the packet capture going from 0 to about maybe about 2.5 seconds here. So not a lot of time. And then we're seeing the amount of bytes as well, which is going up to about 32,000 bytes. So this is our, this is an example of the amount of communication over time going specifically to this IP address. Now we're going to click the plus again, and we're going to create a data series called everything else, right? And this is going to be a pretty cool one, because what we're going to do is we're going to take the same filter we used up here. We're just going to copy it. We're going to go down here and paste that filter in. Now we're not going to use the exact same filter. We're actually going to put an exclamation point in front of it, right? And what that's telling Wireshark, that exclamation point is a negation. So whereas ip.adr equals, and then the address will match everything with that address, by putting the exclamation point in front of it, we're saying match everything without that address, right? So that's pretty cool. So it's using a navy blue color. We're going to leave that. We're going to go ahead and change that to a stacked bar as well and tell it to give us bytes per second. And then I'm going to check that box to enable that graph. So now what we have here is the completed graph, and it shows us a pretty neat thing regarding the distribution of the communication between our primary hosting IP address and the other things that are there as well. That is to say that everything that is red is data being transmitted or received from the web server, the primary web server associated with ESPN.com, and everything else is in this navy blue color. So that's pretty cool. So you can immediately see there's a pretty significant amount of data coming from these other content providers, things outside of the actual ESPN area. So these are things like advertisements, videos, things like Facebook integrations, Twitter integrations, all that extra stuff, those bells and whistles that you see there. So pretty cool way to show this distribution, and a pretty neat way to show the I/O or the input-output related to this specific capture. So there's some cases you might want to use a graph like this. Practically speaking, when you're analyzing web traffic is a really good way to do that. But this also really shows the flexibility of the ability to put display filters in here and then show a certain amount of data, exclude other data, use something beyond a line chart. So here we're using the stacked bar chart to show the distribution of these things. And another great way to look at statistical output related to the packets you've captured. So next I want to leave behind I/O graphs and actually look at something a little different, and these are what we call RTT or round trip time graphs. When we talk about round trip time, we're talking about the time it takes for a response to be received to a particular packet. We'll talk about this more when we talk about latency, but I do want to show you this graphing feature, and I want to show it to you in relation to two files we've already looked at, both downloadfast.pcap and downloadslow.pcap. Now I can get to this graph by going Statistics, TCP stream graphs, round trip time. Now there are a few other graphs here. Round trip time I think is probably the most useful, so I'm gonna. It's really the only one I'm going to show you from that specific list. Now I can pull up this graph, and you'll notice I don't see anything right off the bat, and that's because this graph is directional. So you can basically, it's opened up based upon whatever packet you have selected, and if you don't see any data, you may have to click this switch direction graph. So if I switch direction button. So if I click that, you'll notice it shows me data now. And this is one of those graphs where I think it's really helpful to make it nice and big so you can see it and see what's going on. And what we have here is we basically have a point plotted on this chart. For every sequence number, again, this is based upon TCP data. So for every sequence number, that's our X value. So every single packet is plotted on here, which is why you see it all clustered so tightly together. This is all of the packets in this capture, all 90,000 of them in this case. And on the y-axis, you see round trip time. So we're plotting this based upon time in milliseconds. So these are all pretty quick, right? However, we do have some outliers, and that's the important thing to see. Now, generally in any communication, this is download fast, right? So we see we have some things with slow RTT here, and that's okay. For any communication, you're bound to have some of it that's going to be a little bit of an outlier, right? But so far, really, this spread from 0 to 270 milliseconds, it ain't too bad. That's not bad at all. And you see almost everything is clustered down here at the bottom. It's really, really dark blue down here at the bottom. And this is a pretty healthy looking RTT chart. So what I can do is I can say, I have this download and I want to know how successful it was. I can open up this RTT graph and look at this, and I can very immediately see this was a pretty successful download. There aren't a lot of really large spikes of high latency. If there were, we would see something that looks a little bit different, like a little bit wider here, a little higher number, something like that. But for the most part, this actually looks pretty darn good. I'm not too, this is not a problem. This is the reason it was called download fast is because it was fast and successful, right? So this is a good looking RTT chart for a file download. So with that in mind, what does a bad one look like? Well, let's actually look at an example of that, and we'll, of course, as you might imagine, flip to our download slow file, which is one where we had a download that really wasn't entirely successful. So I'll go ahead and go to Statistics, TCP stream graphs, round trip time. We'll go ahead and make this quite a bit bigger so we can really see what's going on here. There we go. We'll click switch directions here so we get the proper amount of traffic. And of course, keep in mind this is a lot less data points than the other one. So we have only 10,000 packets versus 90,000. But we see some very clear trouble spots, right? So we do have a lot of things clustered down here that look to be received very fast, and that's good. But notice that the spikes we have, they're not little thin spikes that only occurred for just a brief moment, like this one right here that we saw in the download fast. Instead, we see these big sections of spikes here that are a lot wider. And I mentioned that earlier. The width is what's really important here because the width represents sustained periods of long round trip time. And that's essentially latency, right? It's when we have a long swath of time where packets aren't coming back very, very quickly. And so that's what we're seeing here with this width. Now, the interesting thing about this graph is that it can actually be pretty useful when we compare it to the I/O graph we looked at earlier. So let's actually go ahead and do that. So let's go ahead and compare this with the I/O graph we opened earlier when we looked at the throughput of this file. So I'll go here to Statistics, I/O graph, and we'll see we have the same I/O graph we saw earlier. Now let's go ahead and open that up next to our RTT graph. And now we're not exactly on the same time scale here because we're looking at sequence numbers versus actual time as our x-axis. But nonetheless, we're about the same width here, and you can kind of see some clear where some things line up, right? So if we look at the throughput graph up here, we see this big dip right around here. And if you go down, you see here we have this wide swath of increased round trip time. We see another one of those dips right here, and here is another example of round trip time that's a lot higher than we would expect it to be. And we can see that pretty consistently. Here's a dip here, and here's another dip about the same area. Here's a big dip, two of them pretty close together. And of course, here we have two pretty close together increases in round trip time. So there's definitely some correlation here, and this is a good way to show where this download was particularly slow and where the latency issue occurred. With both of these types of graphs, it's really the primary use case for them, is finding latency and slowness in network communications. Now, with both of them as well, with an I/O graph, I can pull this up and pretty immediately see where the issues are. And with RTT graph, I can kind of do the same thing as well. One of them is based upon, at the top at least, number of packets. We could also change that to bytes if we wanted to. And here at the bottom, we're based upon round trip time, based upon TCP sequence numbers. But nonetheless, two different ways of kind of coming to the same conclusion that this download, in particular, this one from downloadslow.pcap, not surprisingly, was slow and full of some issues that caused the file that was being downloaded not to be downloaded in a pretty quick manner. So I/O graphs are great because they're really, really flexible, and RTT graphs are also pretty cool because they can help you spot latency issues. But I do want to cover just one more graph type before we leave this section behind, and I pulled up another capture file to help demonstrate that. This capture file is called DNS Recursive Query Server. And if you know about DNS recursive queries, this should look familiar to you. If not, don't worry, we're going to talk about that when we talk about DNS later. Now, that said, I chose this capture file because it shows a couple different stages of communication that are going on. Particularly, we have a request coming from 172.16.0.8 going to 172.16.0.102. This 102 host then takes that request and sends a new request to 4.2.2.1, and 4.2.1 responds, and then 102 sends data back to 8. So we have this process of recursion going on where basically our DNS server, which is where this was captured from and is the 102 address, is receiving a query. It's asking its own query to an upstream DNS server, getting a response back, and handing that response back to the original client that requested the data, the 172.16.0.8. Now, all that doesn't really matter other than to demonstrate that there's a sequence of communication going on here, and it's really hard to visualize unless you automatically understand how DNS recursion works. Or, it's difficult to understand just by nature of the packet list window doesn't necessarily show that relationship. You can kind of derive it by looking at source and destination, but that's only because these are occurring in sequence and all tightly spaced together. If these were interspersed amongst a bunch of other packets, that really wouldn't be entirely clear. So I want to show you how we can use flow graphs to demonstrate this data a little bit better, how to visualize a little bit better so you can have a better sense of what's going on. To generate this graph, I'm going to go to Statistics and then Flow Graph. And it's going to automatically generate it. And you see it's pretty darn neat. There's not a lot to dissect here, but you see we have this view where we have times on the left, and those are descending. So we start with the first thing that happened here, and the newest thing is down here. And then we go to the right, and we have a different section for each host. So we see 172.16.0.8 on the left, 172.16.0.102 in the middle, and 4.2.2.1 on the right. And we see a comment here, which is essentially data from the info column of the packet list view. So what we're seeing here is actually a nice little breakdown of the communication that's happening. This is everything I just described to you, but it's shown in a way that's much easier to visually represent. So right off the bat, we have a standard query to nostarch.com from 172.16.0.8 to 172.16.0.102. 117.16.0.102 then generates a new query to 4.2.2.1. 4.2.2.1 responds, and then 172.16.0.102 responds back to 172.16.0.8 with the answer to its query. So we have a question being asked. That question is asked to someone else. The intermediary questioner gets a response, and the response is sent back to the original questioner. That's how DNS recursion works, and we'll go into more detail again on that later. But the point is that the flow graph really gives us a pretty unique way of showing this information. It does it by separating the host out into individual lines, and also by including the info detail that's from the protocol dissectors in the info column of the packet list window here as well. So it really shows this a lot nicer and a lot cleaner than we could get in the packet list details. So if there's a communication sequence you're struggling to understand, maybe it's a protocol you're not familiar with, maybe it's a custom protocol, maybe an ICS protocol, something like that, you can look at the flow graph to get an understanding of what you're looking at, and it's a pretty darn neat thing. I'll show you real quick another example of a flow graph from a capture that has a few more things going on. This is a packet capture called Facebook Login, where a user is actually authenticating to Facebook. It's real short. It's only 71 packets, but even with 71 packets, there's a lot of information from the flow graph that's generated that shows us kind of the lay of the land of this capture, or at least the sequence of events. Now I can open this and you immediately see there's a lot more going on in terms of the amount of data. I can scroll for a ways, and there's quite a bit here. But this does lay it out pretty darn neatly, I think. So we can see that our local internal host that this packet capture was probably taken on was 172.16.0.122. It's all the way to the left, and it looks like in regards to this flow graph, all the everything we're observing takes place from that perspective. So it's always on the far left here. So I can look here and I can see immediately we have a connection being established to 69.63.180.173. That is probably one of the Facebook servers, and we see that we have encrypted communication going on here over HTTPS. That occurs for a little while, and then all of a sudden we have a GET request that occurs over standard HTTP for /home.php. So this is to a different server at this point. We're going over to 69.63.190.22, and that communication happens there. So this is happening in the middle of this sequence. That happens for a while, and then communication we see is occurring again between the two original hosts, between our 172 address and our 69 address ending in 173. That communication ends. We see we have a fin-ac sequence going on here. So we have fin-ac, fin-ac-ac. And that kind of is the story of this capture. So that's pretty neat. We can spend more time dissecting this, and we will later on this particular capture. But it's a pretty unique way to show the flow of communication that's going on. After all, this is a lot more intuitive to understand the relationship between these hosts rather than just looking at the packet list window. The packet list window is not really great at showing relationships. It's got a few little helpers here and there, but again, it's called packet list because it is just that. It's a list of packets. It's not a flow of communication. So you have to use other tools like this flow graph to be able to get to the information you need if you really want to understand the flow or sequence of communication and relationships occurring between multiple hosts. That's going to do it for this section on graphs and Wireshark. And we've looked at a couple of different types. We looked at IO graphs, we looked at RTT graphs, and we looked at flow graphs. Remember, the key takeaway here is that graphs can be great for visualizing data when you have a good use case for it. We've talked about several of those here. We'll talk about several more as we go along. That said, don't use graphs as a crutch. I've known people who the first thing they do when they go into Wireshark is pull up a graph and they try to derive all their answers from that, and that's not going to lead you to success. A graph is a useful tool for helping come up with new questions to ask or to answer existing questions. You're going to be using graphs in the context of you'll find some data and you'll pivot to a graph, and then you'll use that graph to pivot to more data. Or you'll start with the graph and go to data from there and pivot to another graph. It's just a step in the analysis process, but an important step, and Wireshark makes it really easy to generate graphs for a whole wide variety of use cases. Again, some of those we looked at here, some of them we'll look at later. But if you get the chance, take a look at some of the sample capture files I've provided and start generating some graphs. Play around with them, do some IO graphs, put some filters in there, play around with them, see what fun you can have, see if you can come up with some graphs that you might want to save and refer to back later. It can actually be a pretty fun little exercise.